right, so let's start. So for the last class, so thanks for coming. And so today we have our last theorem of the course, the Heckman's theorem. Let me recall the statement. Well, as usual, we have a triple M omega mu a Hamiltonian T-space, compact, connected. And to simplify our life, we assume that the fixed point set is a finite set. So then the claim is as follows. So let me denote by n. We have an integral with a Liouville measure of one of the components of the moment map, which is given by the following fixed point sum. So 2 pi to the power n. And then sum of points in MT. And here the exponential factors mu of m xi divided by the product of linear functions, where these are rates of the T action on the tangent space. And this is true for all xi in T such that all those linear functions on the right-hand side make sense. So that's a beautiful formula, but probably, again, to simplify our life today, let's prove the S1 version. So the proof is essentially the same, but the formula is a little bit easier. So for T equal to S1, so the formula is like that, omega to the n over n factorial, exponential of xi mu. Now all linear functions are simply proportional to this one real number xi. So it is 2 pi over xi, and here will be some over fixed points, exponential of xi mu of m. And that's the formula that we discussed last time. Very, very beautiful and interesting formula. So this is valid for all xi non-zero. Yeah, the S1 action. Yeah, I wanted to say if the S1 action is non-trivial, but actually since the fixed point set is finite, the S1 action has to be non-trivial. Right. So our task today to prove this formula. Now there will be several things that we will need to build for the proof. And let me start with the following remark. So let's take M, a manifold, and let's say possibly with non-empty boundary. And let's take V, vector field in M. And let's consider the following operator. Capital D, it will be the Theorem differential minus contraction with the vector field V. And, well, this is an operator. So there are several properties of this operator that we'll be interested in. In some sense, I claim it behaves almost as the Theorem differential. So some properties of D. One property is similar to the Theorem differential. If it acts on the wedge product, well, we know that both the Theorem differential and contraction are derivations or graded derivations, which means that we'll get d alpha wedge beta plus minus 1 to the power degree of alpha, alpha wedge d beta. And this is the same type of property as for the Theorem differential itself. So the second property, perhaps if we compute d squared, so this is d minus iota v squared, and this is d squared minus d iota v plus iota v d. Iota v squared gives 0. And so this is, as usual, by the Cartan's magic formula. So this is the Lie derivative with respect to v. So it's not 0, but, well, it's something that we know very well. That's the Lie derivative. In particular, perhaps one small remark. If we assume that the form alpha is in the kernel of D, then automatically it is annihilated by the Lie derivative of V, right? Since we just multiply, kind of act one more time by D, we get D squared, and this means we get, it's also in the kernel of L of V. Finally, one more remark. So let's say alpha is a form of a mixed degree. And let's use the following, perhaps slightly non-standard notation. So usually we don't integrate forms of degree smaller than the dimension of M over M, but we can also very well do it just by assuming that by definition this is the integral of the dimension M component. So all the other components, they simply, we just assume that the integral vanishes on them. So let's use this notation and let's introduce property 3. So we would like to integrate over M d of some form of the mixed degree alpha. Well, so this in general, this will be a form of a mixed degree, even if alpha only had one component. So this will be integral over M d minus iota v alpha. And this is equal to the integral d alpha minus integral iota v alpha. Right. So now notice that here, according to our definition, so this term will not contribute in the integral because so whatever was the degree of alpha, the degree of iota v alpha cannot be dimension of m, right? Because the top degree forms, they have dimension m. Now iota v, even over top degree form, that's dimension m minus 1. Right? So this is 0 because the degree iota v alpha is small or equal than dimension m minus 1. Right? So this means that what we get is simply an integral of d alpha. Now, well, d alpha may also be a form of a mixed degree. But for the top degree part, which means here for the degree of alpha equal to dimension of m minus 1, we can use the Stokes formula. And for all the other degrees, the integral here and there, they will be 0, right? So the Stokes formula actually works in all degrees, just all the contributions will be 0 on the left-hand side and on the right-hand side for smaller degrees. So this means that for this funny differential, or for this funny operator, I cannot quite call it a differential because it doesn't square to 0. So for this funny operator, there is a Stokes integration formula. So that's perhaps the first remark. Now the second remark is as follows. Now let's say we have an S1 Hamiltonian space. Right? So we have a circle acting on M with the two-form omega and with a moment map mu. And let's consider the form of a mixed degree, omega tilde, which I build simply by adding omega and mu. That's a very strange construction, but you know, so this 2 form is in omega 2, and we can say that mu is in omega 0, which is just C infinity functions on M. So this is a form of a mixed degree, and I can compute the differential d omega tilde. Well, this will be d minus iota v applied to omega plus mu. And well, we're going to have the degree 3 contribution, which is d omega, plus the degree 1 contribution, which is d mu minus iota v omega. Now, very beautifully, this is 0 because the manifold is symplectic. And this is 0 because of the moment map condition. So interestingly, these two conditions, these two equations, they unify in the same equation here. And we have 0 in the end. One more remark. Since we started working with the forms of mixed degree, maybe here I should say, right? So omega tilde is a form of a mixed degree. And it has components omega tilde 2 is equal to omega, and omega tilde 0 equal to mu, right? Now, since we started working with forms of mixed degree, what we can also do, we can define an exponential of omega tilde. So just by definition, this is a sum k 0 to infinity omega tilde to the k over k factorial. Since it is formally defined as an exponential, in particular, it's an exponential of a sum. And so we know that such a power series would satisfy the rule that exponential of the sum is exponential of the first term times exponential of the second term, right? So now we can again write the first term is a power series and multiply it by the function e to the power mu. So e to the power mu is just a function. But this power series, now we know that it will stop somewhere, right? Because these are degrees of our form omega, and the degree of a form cannot be bigger than the dimension of m, right? So in fact here it's not an infinite sum. It's a finite sum which runs up to n. So this is again a form of a mixed degree, and in particular, so this exponential of omega plus mu. So the 0 degree component will be simply exponential of mu. And then while there will be various components of even degree, and the top degree part, so the dimension m degree part, will be omega to the n over n factorial, right? So n was the half of the dimension times exponential of mu. Right. So there is this form of a mixed degree, and the claim is that d of this exponential of omega tilde vanishes. So this is because, recall, d is like a derivation. So we can simply apply the rules of ordinary calculus. And this means there is this formula. So d of exponential is d of the exponent times the exponential. Right? So that just because all the rules of calculus, they still apply. But d omega tilde is 0. So it is 0. Right. Okay. So up to now, it's not quite clear why we're doing all that. But let's remember that there is this nice story. Maybe one more thing before we proceed. Let me introduce a non-vanishing real parameter psi in the game. And let me do the following. Let me introduce d psi, which is d minus iota v. And here I want to multiply v by psi. So let's see where would it change things. So I want to introduce psi here, but then this means I better introduce psi here as well, because otherwise, you know, my equations wouldn't match. So I'll be adding psi's everywhere. So here psi will be as a factor. So here will be psi. So here will be psi. Right? So everywhere I'm adding psi. And this formula is still correct. So you see, you can do a rescaling by multiplying mu by psi, and also by multiplying here this part, this contraction part of the operator by psi. And why do we want it? Because actually, you see now the formulas become even more like the formulas we had before in the theorem. So this expression is very much like the expression that we eventually want to integrate, right? And of course, like towards the end of the today's class, we'll return and rediscuss the role of xi. But at the moment, xi for us is just a real number. Okay. So that's the first gadget we need in the proof. Now the second gadget goes under the name of a real blow up. And so perhaps I will not present the most general definition, but let's think about the following. Consider a real vector space, Rn, and let's take away the origin. So then we know that we can introduce polar coordinates and say that that's the same as the sphere Sn minus 1 times the open ray 0 plus infinity, right? So the picture is like that. So here is our vector space Rn. So I'm taking away the origin. And so here is my sphere. And I parameterize my points as a point. So here an element would be a point on a sphere, and here a positive real number. So the map from here to there is simply multiplying r by n, right? So an arbitrary vector is, so this is n, and this is r times n. Now let me do the following. Let me consider, instead of this space, let me consider the space as n minus 1 times the semi-open ray. So let me close it at 0. Right? So this is still a very nice, smooth space. It has a boundary now. And I can still define a map, sending an element here, and r to r times n, which is now simply a vector in Rn. Right? So, so the boundary let's say, let me not think about this infinity direction. So this will be a semi-correct formula. So the boundary at finite distance of this space, this will be simply Sn minus 1 times 0. And this whole boundary, let me call this map pi. This boundary is mapped to the origin in Rn. So now let's so now let's think of our S1 Hamiltonian space. We know that the fixed point set MS1 is a finite set of points. So here they are, those points sitting. And we know that this is the same as a set of points where V of M is equal to 0, where V is a fundamental vector field, right? So we have our fundamental vector field for the S1 action, and the set of its zeros, that's exactly this set of fixed points. Well, now we know that an open neighborhood of any fixed point is modeled on the space R to N, on which we have a linear action of the circle. So that's the sum of irreducible representations of the circle that we were discussing several times. So now what we can do, we can locally apply this operation to every fixed point. So I would like to apply this blow-up procedure to every fixed point. Since every fixed point is equipped with a model where the action is linear, I can simply just verbatim apply this construction there. So I am replacing a neighborhood of the origin by the sphere Sn-1 times some semi-open interval where I would now include 0. Right? So here I will be putting in, instead of this, Sn-1. So this is times 0, 0 epsilon. Well, the linear S1 action was acting on the unit sphere to start with. So this means that actually here this operation will be S1 equivariant. So the S1 action leads to the blow-up. So perhaps one more drawing. So I've got my manifold M. So here is this S1 action, fixing the points. And now we are making a blow up at each of these fixed points. So the resulting manifold, let's call it M hat. It still has an S1 action. So there is this projection pi. So the blow down map. And this pi, it is identity outside those boundary components. And each boundary component here, this which is, we know it is a sphere Sn-1, it is mapped back to the fixed point from which we built this blow up. So pi is S1 equivariant, and well, dm hat will be equal to disjoint union over the points in the fixed point set. And here we can say sphere of dimension 2n minus 1 with the index m, right? So these are these boundary components. You see, that's why I didn't pay attention to what happens at plus infinity, because eventually in my construction this part disappears. I only get my boundaries from the finite part of the construction on Rn. Okay. Perhaps one small remark. So here on the manifold M, we also had a two-form and a function. Obviously, if we want, we can pull them back to M hat. So we have pi star mu, which is simply a composition of mu and pi, and this is a C infinity function on M hat, and pi star omega is a two-form on M hat. Now maybe like a small test question. What do you think will happen if I try to evaluate this pi star mu, for instance, on this boundary component?
Just get the value of the
Yeah, it will just get the value of this fixed point. So this is M, and here pi star mu of any point on the sphere is just equal to mu of M. What about the two-form? What's the pullback of the two-form to the boundary components?
0, maybe?
Yeah, of course, it's 0. So we're pulling back a two-form from a point. Any two-form on a point is 0, whatever it is. So when we pull it back, so it is 0 on this, if we restrict this pullback to any of the boundary components. Okay. So the next gadget, actually the last gadget that I need. So this is a theorem due to Berlin-Verne, and it says the following. So suppose that M is a compact connected manifold equipped with an S1 action. And let's assume that the fixed point set of the circle action is a finite set. So furthermore, let's assume that alpha, and here, well, let me write several versions. So a form of a mixed degree and a polynomial in one variable, or maybe a C infinity function in one variable with values in differential forms. You know, so this is, if the function is polynomial, then this is the same. But in principle, kind of for me, I don't kind of later on, we'll talk about polynomial versus non-polynomial story. But let's say at the moment we keep both options open. So in any event, it's a function in one variable and a differential form on M such that dig psi alpha is equal to 0. And here maybe I should say for all psi. For all psi in R. So then the following is true. should add here compact connected oriented manifold. So the integral of M of the top dimensional component of alpha is equal to 2 pi over xi to the power dimension of M over 2 times the sum over the points of the fixed point set, and here the 0 degree component of alpha computed in M divided by the weights. So maybe kind of I need to make several remarks about this formula, but first let me ask a test question. How do we know that the dimension of M is even? What if it's odd? Right? Why does it kind of make sense?
I'm sorry.
Uh-huh. Yeah, we actually know that, okay, let me put it differently. We actually know that the dimension of M is even. Why?
I mean, do we assume M is a Hamiltonian?
No. No. No, we don't. Right? M is a manifold. It has an S1 action. So the fixed point set is a finite set. And then, well, the other assumptions is about this differential form alpha, right? So do we know that the dimension of M is even?
Maybe the fact that the fixed point set is finite.
Right. I think actually, I'm probably lying. So we actually don't know that the dimension of M is even, right? But if the dimension of M is odd, then but we still know something. Still, the right-hand side kind of makes sense, and we don't need to take square roots. So if the fixed point set is non-empty, right, then at any of the fixed points, we can have we'll have this normal form, right? So the sum of irreducible representations of the circle, and there are no trivial ones, because otherwise the fixed point set cannot be finite, right? So this means if this is the case, right, then CMM at a fixed point, so will be sum of R2s with some non-vanishing weights as an S1 representation. But if this is a sum of R2s, the dimension has to be even, right? The dimension may eventually be odd if the fixed point set is empty. But if the fixed point set is empty, then we still don't need to take any square roots, because in the sum there are no terms. Right? Then the right-hand side is just 0. So if so then the fixed point set is empty. So that's the first remark. Now the second remark, in principle, this alpha is a form of a mixed degree, right? So it's a sum of many components. And this formula, interestingly, it relates the integral of the top degree component, so of the component which has the highest possible degree, dimension m, to the zeros component, to the component which is just a function, right? So it's a little bit in the style of a residue theorem or Cauchy residue formula, where you have an integral of a curve which is related to some singularities of the function that you have inside. So that's a little bit similar. Note that the dimension can be very high, so in principle, right, there is, we don't kind of, so it looks a little bit surprising. Of course, the only thing which relates different degree contributions here is this equation, right? So that's this equation which somehow links different degree contributions and which might ensure that this holds true. So let me remark that actually the Verlanders theorem implies Düstromet Heckman. Verlanders implies Düstromet Heckman. So why is that? Well, we can so if we now do deal with a Hamiltonian S1 space, then we can choose alpha to be exponential of omega tilde. So we decided this is the sum over k from 0 to n. Now omega k over k factorial exponential of psi mu. Right, we actually know that d psi alpha is 0, that we already established before. An integral over m of the dimension m component will be integral over m omega n over n factorial exponential of psi mu, because that's the dimension m component. And on the right-hand side, we'll have 2 pi over psi to the power n, sum over fixed points, and here alpha 0 of m divided by the product of weights. And well, so here we have 2 pi over psi to the power n. Sum of the fixed points. And well, this 0 degree component, so k equal to 0 component, that's simply exponential psi mu of m. And here we divide by the weights.
So there's also a product over the weights there?
Oh, yeah, product, sorry, yeah, product over the weights. Right. Right, so this surprising Düstromet Heckman formula, it follows from equally surprising Verlanders formula. So basically, now we reduced the Düstromet Heckman formula to the Verlanders formula. What remains to be seen is how to prove Verlanders. Okay, so let's have a break, and after the break, we finally prove Verlanders and maybe make a little bit more remarks on how it's related to some bigger story which is called equivariant cohomology. Perfect. So let's do the proof for the Verlanders theorem. All the fixed points, and there is a blow-down map pi, the projection from m hat to m. And the first step that we can do is as follows. So let's denote by alpha hat the pullback of alpha. And note that the integral that we are interested in, so the integral over m of the top degree part, we can also write it as an integral over m of alpha. It doesn't matter so much whether, because all the other components, they will not contribute. And now notice that this is the same as integral of alpha hat over m hat. So that's because the difference between m and m hat, this is in those points and the codimension 1 submanifolds. So over an open dense subset, this is just the identity map, this blow-down map. So this means that for the integral, this will be a negligible set over which measure 0, say Lebesgue measure 0 set. So this means that the integral will not change if you replace m with m hat. So this is m, this is m hat. So now one more remark. We know that there is an S1 action which leads to m hat. And the only fixed points of the S1 action on M, these were the points where we made a blow up. So we replaced them by unit spheres. And on those unit spheres, the S1 action has no fixed points, right? So this means that all in all, on M hat, there are no S1 fixed points. Is actually equal to 0. So let's denote by V hat the fundamental vector field of the S1 action on M hat. So this means that V hat is nowhere 0. Right? Now let's look at the equation d psi alpha equal to 0, right? So that's the equation which says that d minus psi iota v alpha is equal to 0. So let's pull back this equation to m hat. So let's apply pi star to it. So we'll have 0 equal to pi star d minus psi iota v alpha. And that we can rewrite in the following way. Well, of course, d commutes with pullbacks. So this is d pi star alpha. And now what about iota v? So we know that the map pi is S1 equivariant. Since it is S1 equivariant, this means that we can commute pi star with iota v by replacing v by v hat. Right? So the corresponding vector field on m hat is v hat. So this is minus psi iota v hat pi star alpha. So and this is possible because I is S1 equivariant. So all in all, we get d minus psi iota v hat alpha hat. So let's denote this operator by d hat psi. So that's a similar operator on differential forms on m hat. And we see that this alpha hat, the form that we are integrating here, it is in the kernel of d hat psi. Now, a very interesting trick invented by Berlin and Verne is as follows. So we're still lacking tools to prove the theorem, but now finally that's the trick which allows us to do it. So choose an S1 invariant metric G on the space M hat, and consider the following one form. So we take the length of the vector v hat at a given point, and then consider pairing of a vector with this vector v hat. So this is well defined because v hat is a nowhere vanishing vector field on m hat, right? Otherwise this would not have worked. Perhaps let me add a minus sign here. Right, let me add a minus sign. So this is a one form on m hat, and consider d psi of this one form. Well, this is d minus psi iota v hat gamma. So let me write it in the following way. So there will be some d gamma, well, whatever it is, the de Rham differential, plus psi. And now I need to substitute v hat into this form. Right, so what I get is g v hat divided by g v hat. And this is equal to 1, right? So I'm getting d gamma plus psi. So this is already kind of interesting, right? I'm getting something proportional to psi, but otherwise psi is here coefficient in front of 1, right? So we see that this operator acting on something, it more or less gives you 1 plus corrections. Now let me make an even more radical step. Notice that I can now invert d psi gamma, assuming that psi is non-vanishing. So this is psi plus g gamma minus 1, and this will be something like this. I can write it as psi minus 1, 1 plus psi minus 1, g gamma minus 1. And here I can again just use a power series for 1 plus x to the power minus 1. So this will be psi minus 1, sum over k from 0 to infinity. How is it? Minus 1 to the k, psi to the power minus k, g gamma to the power k. Right. So in fact, this will so this sum will also be finite, right? It will not be an infinite sum because this is a two-form. So this means that actually this is a finite sum up to dimension m over 2, whatever the integral part. Right. So this is a well-defined differential form if psi is non-vanishing. One more remark. Dig psi gamma. We know that this is minus psi LV hat gamma. And since G was S1 invariant, this means that the Lie derivative with respect to V hat, so with respect to S1 action, will be 0. So that's because G is S1 invariant. Now I'll leave you as an exercise to show that if dig psi of dig psi gamma is 0, this implies that dig psi of dig psi gamma minus 1 will also be 0. So usually we don't invert differential forms. But now we have a tool to do it. So this guy is well defined, and then all the normal calculus rules apply. Okay. So one more move, but that's probably almost the last one. So let's introduce one more differential form, and it will be gamma times dig psi gamma minus 1. So this is a differential form of mixed degree on m hat. In fact, this will be a form of odd degree. So gamma is a one form. Dig psi gamma, we see it is a sum of differential forms of even degrees because d gamma is degree 2. So it's a sum with some coefficients of d gamma to the power k. So this is a form of an odd mixed degree. And notice that dig psi beta is equal to dig psi gamma minus 1 minus gamma dig psi gamma minus 1. So the second term vanishes because dig psi of dig psi gamma minus 1 we decided was 0. And this term is simply equal to 1. So this is a kind of shocking equality. So this, whatever this differential or this operator acting on beta is simply equal to 1. So that's really the key observation, that this is possible. Obviously, it would never be possible if D were just a de Rham differential. And of course, it all works if psi is non-vanishing, because you see this d psi gamma minus 1, right? It's a kind of polynomial in psi minus 1. So here, psi non-vanishing is an essential feature. So now let's return to our integral. So we would like to compute the integral of m hat of alpha hat, and we rewrite it as an integral of d psi beta alpha hat. Well, of course, d psi beta is simply equal to 1. Right? Now we rewrite it as an integral of d psi of beta wedge alpha hat. And this is because, recall that d psi alpha was 0, and I should probably write d hat, right, everywhere. But I was forgetting to write d hat. Right, so this was... So there is a finite number of d hats. So that's because d psi alpha implied d hat alpha hat equals 0. Well, now we use the Stokes formula. So that's the integral of the boundary of m hat of beta wedge alpha hat. Now the boundary of m hat, that's this disjoint union of spheres, which correspond to fixed points. So this means this is the sum over fixed points, and here that's an integral over the particular boundary component of beta wedge alpha hat. Now let me recall that alpha hat, that's the exponential of pullback of omega times exponential psi pullback of mu. Now recall again, what happens when we restrict it to the boundary component? So we already discussed it once. So do you remember the result? So what happens with omega? It vanishes, and mu acquires the value of the corresponding fixed point. So actually this restriction is simply psi exponential of psi mu of m. So actually when you restrict this, this mixed degree form, you just get not even a function, you get a number. Right? So actually this is equal to the sum. What am I saying? Sorry. Forget it. One more time. So alpha hat is equal to pi star of alpha and is equal to pi star sum from 0 to dimension m of alpha I. You see, I forgot that we actually proved in Verlanders and not Theorem at Heckman. So there were no omegas, no mu's, nothing like that. Okay. So so we're supposed to say what's the restriction of alpha hat, which is pi star of alpha, to the boundary component, which is a blow up of a point, of a fixed point. So now, kind of, do you want to do the same type of analysis, but applying to this story? So first of all, what happens to forms of to the components of non-zero degree? They will vanish, of course, if you kind of because you first have to restrict them to a point and then pull back from a point. When you restrict a form of non-zero degree to a point, it already vanishes. Now, like pulling it back. So they will all vanish with the exception of the 0 degree part. The 0 degree part, when you restrict it to a point, it's just a number. It's a value at that point. Now you pull it back. It continues to be a number, or a constant function, better say. So this is equal to alpha 0 of m. Right. So the analysis is the same, just the wording is different. So again, so this thing, it's just a number on each of the boundary components, or a constant function. So we can take it out of the integral, and what remains is this. So these are integrals of the restriction of beta to s to n minus 1 m. So that's the answer. Now, what remains to be seen are what are those integrals of betas. Right? So this will be our last calculation. Now I need to compute. I need to compute these integrals. So note that here there is no information about alpha, right? All the information about alpha is already here. So what's the information that we are looking at here? Well, that's the information about the form beta, and the form beta is constructed by choosing some metric somewhere, but we of course hope nothing would depend on the metric, and the important thing is the S1 action, right? So now the computation of those integrals, even though it's possible to do it directly, we'll do it by a trick. On the neighborhood, so the neighborhood of a fixed point, we can model it on the neighborhood of the origin in the space, in the tangent space, TMM, which splits into the direct sum of S1 representations with given weights. Let's say Nj at the point M. And here we can, let's introduce local coordinates on the on those R2s, and it will be convenient, I think, to introduce polar coordinates. So let's say here we'll introduce polar coordinates. So this is the copy R2 with the weight Nj, and so we'll use polar coordinates Rj theta j. Polar coordinates. And in these polar coordinates, let's do the following. I will build a differential form alpha hat for which I know the integral, and then this would evaluate for us those integrals of beta. So the S1 action here works as follows. So phi maps Rj theta j to Rj theta j plus Nj phi. Perhaps I drop for a while this index m, which corresponds to the fixed point. At the moment, I'm only looking at one fixed point. So let me also introduce a function chi from R to R, and it will be a smooth function with compact support, which is, let's say, symmetric and equal to 1 at 0, and then equal to 1 near 0, and then descending and equal to 0 outside for sufficiently large R. So let's take such a function, and let's consider the differential form dig psi, which will be, say, so I choose one of those j's, and I take minus chi of Rj d theta j. Right. So in fact, so this, such a form, right. Okay. Yes. So let me compute this dig psi of such a form. So this will be what? The de Rham differential. So this will be minus chi prime Rj, drj wedge d theta j. And then I should add to it psi chi of Rj. And now we make an insertion, right, of the fundamental vector field. So the fundamental vector field will give you this just Nj, right? The fundamental vector field is Nj times d over d theta j, sum over all j's. So that's what the formula says. So times Nj. Right. Notice that this differential form actually, first I defined it on m hat, but it's actually a differential form on m, because you see, so this is just a constant, or this is just a function of Rj, which is a smooth function. So this is a pullback of something on m, and this guy, the derivative of chi, it vanishes here, right? It's only non-vanishing somewhere there. But this part of m hat and m, they are the same, right? So m and m hat, they are only different here. So in fact, this is a well-defined function on m, and well-defined form on m. And what I can do now, I define alpha to be a product over j of this of these forms, right? So so if we think of our manifold, here is the fixed point, and this form alpha, it is supported on some small neighborhood of M. So after that, like the chart ends, but our form has compact support within this chart. So it's defined in the chart, but then we can think of it as a form on M. Right. Now, a simple exercise is to prove that dig psi alpha is actually equal to 0. So let's discuss why this is true. So of course, this is a product of dig psi's of something. So when we take dig psi of alpha, this kind of dig psi would hit one of those dig psi's. So we get dig psi square. Dig psi square is not necessarily equal to 0, right? But this is a Lie derivative for the fundamental vector field. But these forms, they are all S1 invariant, right? So functions of Rj are S1 invariant, and d theta j is also an S1 invariant one form. So all these forms, so that's because LV of these forms vanish. Right. Okay, very well. So we can now apply our formula. So this was also equal integral over m of alpha. So we can apply our formula to this particular alpha, right? So first of all, the integral over m of alpha. So that we can actually compute by hand, because you see, so this is the same as an integral over m of the top degree part. Now, what's the top degree part? That's just a wedge product of all of those forms, right? So integral over m product minus chi prime rj drj wedge d theta j. So that's the same as simply product of integrals over R2 minus chi prime rj drj wedge d theta j. Now these integrals we can easily compute, right? Just by the fundamental theorem of calculus. So this is equal to the product over j, chi j at infinity minus chi j at 0, and here minus sign, right? Minus plus times the integral over d theta j, which is 2 pi. Now this is 0, this is 1, and we get 2 pi to the n. Okay. So in fact, in this case, we know the left-hand side. The left-hand side is simply 2 pi to the n. Now we need to know what is alpha 0 of m. Now what is alpha 0 of m? For that, we just need to take a product of the degree 0 parts, right? And when we compute it at m, this means Rj is equal to 0. This means here we get 1. So this is the product of j, xi j of 0 times nj. And this is equal to xi to the power n, product over j of nj. So finally, what about this integral? Now there is only one term on the right-hand side, and kind of this equation now tells us that the integral of beta of S2n minus 1m is equal to what? To 2 pi to the n divided by xi to the n times the product over j and j of m. Right? So just from the comparison of the left-hand side and the right-hand side, that's what we get. And that's the formula that we wanted. Let me finish the class and the course with the following remark. And actually, that's a kind of idea which leads to another proof of the Heckman theorem. Rick, could you control my pronunciation? Was it? So the idea is as follows. So recall that we were looking at dig psi equal to d minus psi iota v acting on differential forms on M, and then we were thinking of them maybe as some smooth functions of psi, but let's think of them as polynomials in psi for a moment. This is, you see, this is not our case in a Heckman theorem. That's the problem. But let's still think for a while about it in terms of polynomials. So actually, we notice that this is a little bit a strange situation. We have these forms of mixed degree. We have the operator of a mixed degree, which is all in all somewhat strange. We are used to things in, say, theory of differential forms to be graded. Well, we can actually correct it. Let's do the following. Let's simply introduce here a new degree. So a degree of alpha times psi to the power k, the degree in terms of psi. So this actually means that we are saying that this variable psi is all of a sudden of degree 2. This sounds strange, but on the other hand, what happens here? So the degree is plus 1, and here the degree is 2 minus 1 is also equal to plus 1. So then this operator is again a homogeneous operator of degree plus 1, which certainly sounds nice. Now, let's consider inside this space of equivariant differential forms, which will be simply S1 invariant forms and polynomials on psi. So on this space, we still have an action of dig psi, and dig psi square is minus psi LV. But now on S1 invariant forms, it is simply equal to 0. So dig psi now defines a differential on this space. So let me cite the following theorem of Cartan. I will state it and then I explain a little bit what it is. So Cartan proved the following. So let's consider the cohomology of this complex. So we take the space of S1 invariant forms, which are polynomials in psi, with respect to this differential dig psi. So Cartan proved that this is isomorphic to the so-called equivariant homology of M with real coefficients, where I should say what this is. So S1 Homology of M. And the idea is as follows. One is introducing what is called a universal S1 principal bundle. ES1 over its base BS1. Here there is an S1 action. And the characteristic feature is that ES1 is a contractible space. So it's not unique, but kind of in the homotopy theory, you don't necessarily need uniqueness, but you can choose any such an S1 bundle where the total space is contractible, and HS1M is defined as the homology of the product of M times S1 divided by the diagonal action of S1 on the two factors. It turns out it's well defined, so any model of ES1 which satisfies these conditions would give the same homology, and that's the definition of the equivariant homology, S1 equivariant homology of M. Of course, Curtin was not looking for the meaning of this complex. So the Curtin's theorem was that there was this object which is kind of complicated because you need to use some model of ES1 and so on. And Curtin's theorem originally read in the other direction. So take this complicated object, and in fact over reals you can compute it using the equivariant differential forms where you take this very strange assignment that the degree of psi is equal to 2. So this is a kind of entry point to some other theory which also kind of gives you a different, in some way different proof of the localization theorem. But that's probably not for this class and not for this course. Well, I think that's a good point to stop. Thanks a lot, and well, good luck at the exam.